Hello and welcome. Today we're going to talk about computing volumes with integrals. And we're really, of course, talking about, there's many ways to compute volumes with integrals, but we're really just talking about single variable integrals here. Just so everyone knows, in later semesters we'll learn more exotic ways of doing the same idea. But let's first go back to what an integral is, right? So we always thought of an area under a curve as that prototypical approach to understanding the calculation of an integral, the idea that we have some function f of x, which is equal to y. And what we do, of course, is we break up the interval into smaller intervals like so. And if I look at one of those rectangles all by itself, of course it has a delta x, and that's the width. And then there, of course, that's going to be y is equal to f of x I star. And that's going to be, of course, the height. Okay. And that'll be delta xi. And the idea, of course, is that if you have an integral from a to b of f of x dx, what you really have here is just a sum of heights times widths. And then, of course, you're just taking the limit. Oh, I should have given myself more space. Let me actually just take a little time to redo that. We're actually taking the limit, of course, as the widths go to 0 of the sum of heights times these widths. Okay, so that's the schematic or the sort of basic conceptual idea. And what I'd really like to highlight here, though, is together, a height and a width together, when you multiply them, you basically get areas. So another way to write this same thing is the limit is the widths. The widths go to 0 of the sum of areas. Okay. All right, so it begs the question then, what can we do to generalize this process? And the thing I really want to highlight here is, of course, does the sum always have to represent areas, i.e. a height times a width? And the answer, of course, is no. If you can sum areas, you can also sum volumes. You can sum lots of different things. The units, the mathematics works independent of the units. So in fact, you can sum anything in an integral if it converges. That's the only rule. Okay, all right, so to see if we can get a sense of how this works, what I want to do is, so what we want to do is see if we can find a way of adding up other things. All right, so what are we going to do now here is now we're going to think of basically, ask the question, what can we sum in an integral? And the answer is we can also examine a thing like this. Like let f of x be a measure of area of some object. Well then, if that's an area, maybe even say it's in meters squared just to be specific, right? Then of course delta x is going to be a width, just like before. And then of course when I do my summation, I get an f of x I star times delta xi, I equals 1 to n, like that. Really what I'm doing is I'm basically like adding up a bunch of volumes. Okay, so the total result then, of course, will be some volume. Right, so one object or one kind of perspective on this is we can think of basically as f of x as a cross-sectional area. So if we have x on this axis, let's say we put y on that axis, or we can put y on this axis here, we'll put z there for whatever. And the idea then is, of course, if I am at a specific x value, x equals a, let's say, we can draw like a shape, and that represents f of x at a, and that represents this area, this cross-sectional area at that point in time. Now, if I go to another place, like say here, x is going to be some point a little later on, and maybe the area is some different shape, or there's some shape there, but then there's also some sort of f at x there. And then, of course, I can go all the way here to maybe to b, and maybe we have some other area that's sitting right there, f of b, right? And together, the whole thing forms some sort of solid shape like that. And the question is, what's the volume of this? Well, the volume is going to be equal to the integral of from a to b of f of x dx. And what we can think of, basically, is that these two pieces there are basically a tiny slab of volume. So from before, we had that cross-sectional area here, like that. And then we're going to put on it, maybe I'll put it in red. That can be a tiny dx, a little tiny thickness. A thickness, right? Okay. So that's the area right there. And that's that thickness. And of course, what we're doing, of course, here is summing these little slabs of volume. Okay, so that's the concept. Let's go to a really specific example now. All right, so we can actually talk about kind of the classic example, that is of a solid of revolution. All right, so a solid of revolution is, we can say let f of x be the silhouette of the radius of an object about the x-axis of revolution. So, for instance, we can talk about maybe a shape like this. What we're going to do, of course, this is my f of x shape here, that silhouette. I've kind of drawn it to be kind of like a pot that you would throw in a pottery class, like that. And it has a radius, right? And it has some volume, so it's again like a pottery kind of thing, and it has a radius there. And there is that cross-sectional area, all right? So here, f of x equals the radius at x equals at x. Okay, right, so if f of x is that radius, okay, then of course the area of x is going to be pi r squared, or pi f squared x, okay? Right, and of course that volume slab, well, that's going to be pi f squared x dx, okay? And we're going to sum up. And of course, if we start here at x equals a, and here goes to x equals b, then the volume of the solid of revolution is going to be the integral from a to b of pi f squared x dx. All right, so that is a formula we'll try to remember. And then what we're going to do now, let's actually do an example. Of course, we're going to do a classic. Let's actually find the volume of a ball. Okay, so the volume of radius r. So the volume, we know a formula for that. It's actually 4/3 pi r cubed. All right, let's derive that formula. And we're going to do it with an integral. And of course, if I've got here's my y height, and here is my x-axis, then I know I'm going to go out to r, and I'm also going to go out to negative r. I know the ball is going to be this shape right there. That's the silhouette, and of course we have another one down below. Right, and we know that each one is going to be a little slab like that, a little cross-sectional area. Of course, we know that r squared is equal to x squared plus y squared. That's the equation for the circle. Okay, and that of course means that y, of course, is going to be that radius. Right, so y is going to be equal to square root of r squared minus x squared. All right, so if that's our radius, then we can put in our equation. So our volume is going to be the integral from negative r to r of pi r squared dx, and r of x is going to be this function up here. We can think of that as r of x, negative r to negative r of pi, and now we're going to put it in. No, I shouldn't call it r of x. I'll call it capital R of x. There we go. Just to contrast it from lowercase r. All right. There we go. The square takes away the square root. And of course we get pi r squared. That integral, I can break it up into two integrals here. Of course, this one is going to be pi r squared. That's a constant with respect to x. And then, of course, we have minus x cubed over 3 negative r to r. We'll keep going. Of course, we have pi r squared of x, which x is going to be evaluated at r, and minus a minus r, minus x over, or pi over 3 times r cubed minus a minus r cubed. Okay? All right, so now all we have to do is put this together. It looks like we have 2 pi r cubes there, minus 2 pi over 3 r cubes there. This is going to actually be 6/3 on this side. And of course, we're left with 6 minus 2 gives us 4. 4/3 pi r cubed, which is the classic formula we've probably remembered from geometry class or algebra class. In some place we've learned that the volume of a sphere is 4/3 pi r cubed. So that's a great example of a problem that, or a problem that we probably took as a fact of that we took as a just a fact of that you're supposed to memorize, and now of course we've been able to construct it using this classic formula. All right, now let's do another one. I want to talk now about let's talk about a parabola. Let's talk about y equals x squared. So this one's going to be a little different. Put x there, put y there. 1, 2, 1, 2, 3, 4. So this is sort of going to be like if I do a solid of revolution around that curve, it's going to look like that. And now I want to actually find out what the volume of this is here. Okay, so it's sort of like the volume of a champagne flute is sort of what it looks like to me. So here, though, our slabs of area are actually on a horizontal plane. And so, of course, we're going to be integrating along the y-axis. All right, so this is pretty neat. Okay. All right, so let's do it. Let's integrate along this y-axis. All right. Of course, y is going to start at y equals 0, and I think the way we set it up, x is equal to 2 here, so y is going to be equal to 4 at the end. So know that the volume is going to be equal to the integral of 0 up to 4, and we're going to have it going in the dy direction. We're going to be integrating up all those different things, okay? And so all of our little slabs of volume are all going to be dy thickness there, okay? So the next thing to get, though, is we have to figure out what that radius is at every point. So we have to measure that. Okay, so we know that that radius is really going to be the distance from the y-axis to y equals x squared. All right. Well, y is fixed. We can always fix the y value and say, okay, if I know the y value, because we're integrating with respect to y, we're actually fixing each y value and checking out and seeing what the cross-sectional area is there. So y is fixed. All right. And so what that means is, of course, I can take the square root of y and get x. All right. And so x is that distance traveled as we go from the y-axis to wherever the edge is. Okay, so that's what it is. All right, so it's going to be pi square root of y quantity squared. Okay, so that is going to be that radius. All right, I think we can integrate this one fairly straightforwardly. And that, of course, is going to give us a y dy pi y squared over 2, evaluated at 0 to 4, and we get pi 16 over 2 pi times 8. Okay, so that's the volume in that parabola cup or champagne flute, whatever you want to imagine there. Okay, all right. Now let's do yet another example. So far, thus far, it was solids of revolution. Solids of revolution. Okay, so basically we're taking disks. We're doing disks with variable radii as x or y is changed. Basically everything that you can make in pottery class. Pottery class on the pottery wheel. So these sort of solids of revolution, and we compute the volumes of them. But, of course, we can compute lots of volumes of shapes involving, slab-like volumes. So let's talk about another example, that of the pyramid. All right. So the pyramid, again, I can draw it like this. We'll put an X there, or actually put an X there and a Y there. Okay. And we're going to make it unit length across. Like that. So it's going to be negative 1/2 out here, a positive 1/2, so on and so forth. Negative 1/2, or yeah, positive 1/2 there, and so on and so forth. And of course, what we're going to do is take it up to a point and make a pyramid out of it. Right, so the slabs here are going to be perfect squares. So they're not going to be disc shapes, but rather perfect squares in each one. I'll just do it in different colors here to kind of contrast them all. And so on and so forth, right? So we're going to add all those up. Of course, this is on that z-axis. So our integral is going to be something dz. All right. So we don't know what our a and b are yet. We don't know what that is, and we don't know what goes here yet, right? So one thing I'd like to highlight here in this chapter and this new stuff that we're doing is we're building integrals that do jobs, right? So it's not necessarily the integration that's that hard. Oftentimes it's fairly straightforward. But what's really interesting here is that we're building an integral that does, it's the building of the integral that is the challenge. And so we have to sort of put together every piece using geometry and whatever mathematics that we need to know. Okay, right, so let's, again, we have this unit length side of 1, right? So if I were to look at it this way, I have to just figure out how tall the pyramid is. What's the height? If the base is 1, okay. So, and we're also going to, of course, say that the sides lengths here are 1. So this is going to be an equilateral pyramid. If you look at the profile, it'll be a perfect equilateral triangle, 60 degrees on each side. Okay, And so with that, we should be able to figure it out. Okay. All right. So we still have to figure out that height, and that's actually pretty easy to do. If I take just half of that pyramid, of course, that's going to be the height there. This is going to be 1, and that's going to be 1/2, right? And so with Pythagorean theorem, we should be able to get it. It's going to be 8 squared plus 1/4. 1/4, yeah, is equal to 1. All right, so that means 8 squared is equal to 3/4, right? Or h being equal to the square root of 3 over 2. All right, so now we know a good fact. We know that our integral is going to go from 0 to square root of 3 over 2 dz, and now we have to figure out what the area actually is, right? Because once we have the area, we multiply it by the little thickness of the slab, and then we should get the volume. Okay, cool. All right, so if we've got that, then the next thing we have to do is figure out, okay, so the thing we need to do is, and I'll do this in a different color, as z is moved up, so if I think about it this way, is if my z value is right here, I have to figure out the length of that line, the side length of the pyramid the side length of the pyramid, maybe we'll give it a name. We're going to call it L of z changes. At z equals 0, we know that L of 0 has to be 1. And at z equals root 3 over 2, we know that L of root 3 over 2 has to equal 0, right? All right, and we know that it's going to be linear, so we should be able to figure it out, that the maybe it's even best to just turn it on its side like this. I'll do it in a different color. We have 1/2, and then we have that root 3 over 2. So I need to figure out basically, so this is the z-axis here. I have to figure out what the height, what this is, or what that is there. And it should be pretty easy. We can call it w just to give it a name. And it's going to be 1/2 minus 1 over root 3 times z. Okay, I think that should do the trick for this. And we know that when z is equal to 0, we're going to have 1/2. And when z is going to be equal to root 3 over 2, we're going to get 0, right? So we know here that L of z is just going to be 2 times w of z. So we're going to have 1 minus 2 over root 3 z. All right, so that's the side length. So if I was to kind of draw a picture here, I'll make a nice thick line there. That's going to be my L of z, that length. Of course, if I have 2 of them, I put them together, and the area of that slab is going to be L of z squared. All right, I think we have it. Now all we have to do, and I think I'm going to have to go to another page to figure this one out. I can now add it all up. I'm going to have that volume is going to be equal to the integral from 0 to root 3 over 2. of 1 minus root 3 over 2 z quantity squared dz. Let's see if I got that right. Oh, nope, I didn't. I inverted something I shouldn't have. That was going to be 2 root 3. Okay, 2 over root 3 there. Okay, so this is my integral now. So again, I've built the integral. Now the final step is just simply to add it up, to actually add up all these little slabs. And we're going to have 1 minus 4 root 3 over 2 over, yeah, 4 over root 3 times z plus 4 over 3 z squared dz. We're going to get z 0 to root 3 over 2 minus 4 over root 3 times z squared over 2 from 0 to root 3 over 2. And then finally, plus 4 over 9 z to the third power of 0 to root 3 over 2. Minus, we can take the 2 out. We're going to get a root 3 over 2 coming out of that, right? I believe so. 3 to the 3 halves, all over 8. That becomes a 2. It's also worth noting that 9 is actually 3 squared. So 3 squared over 3 to the 3 halves, well, that's actually going to be 1 over root 3. Okay. So those go away. And we end up with 1 over root 3 times 2. All right. So there we go. That was our volume of a pyramid. I hope that was satisfying. Yeah, not much to say about this, but I think that was a good video. And again, the key here is, the whole point here is that we're building integrals. Building integrals, that's the challenge. Okay, thank you very much.